Hello everyone, welcome to Gradeup. Let's continue this course on machine design. In the last class, that was the second video. The first one was the introductory video. The second one with which we started our course was the design against static load. In that lecture series, or in that lecture specifically, I told you that there was nothing much to be explained again, because that whole topic or that whole chapter was covered in a very much detail in the subject of strength of materials. Okay, so because the first and the foremost assumption that we did while solving the problems or while analyzing the topics of strength of material was that the force should be all the loads and the forces that are acting on any member, they must be static. So the design against static loading is nothing but the whole subject of strength of material. So we did not emphasize much on that topic in this subject. Okay, so but now this topic, this lecture on fluctuating load, the design against fluctuating load, that has to be looked upon in a greater detail, because this is a new topic. Because the fluctuating loads, we haven't introduced the concept of fluctuating loads anywhere before. So now we will be introducing it, and we will see that how we use this concept, or how we use this, how we design the components or the members which are subjected to fluctuating loads. Okay, so let us begin. First of all, we need to understand few terms. Okay, because without them we cannot understand the concepts of fluctuating load and also their designing. So let us begin with some of the important points or important concepts. The first is stress concentration. We need to understand what is stress concentration. Okay, first we will read out the definition, and then I will make you explain with the help of the diagrams that are given here that what do you really mean by this term stress concentration. Okay, stress concentration is defined as the localization of high stresses due to the irregularities present in the component, okay, and abrupt changes of the cross section. That means, see, if this is a member, this is a rectangular bar, okay, so, and there is a hole cut out in the middle. In the middle there is a hole cut out in this rectangular bar. Okay, if you see this section, this side section, if you see at this corner, the stresses that are induced, if there is some load acting, the load hasn't been shown here, but suppose there is some load acting on this, so the stresses that are present are all equal. Why? Because the area of cross section is same, and if the load applied is also same throughout the cross section, then the stresses induced will be same throughout the cross section. Okay, this is the nominal stress or the normal stress that we are getting. But see, due to this hole, if we cut out this section at this middle region, okay, then what will happen? See, at this section the area is more, okay, at this section the area is more, and as we come this side the area decreases. Okay, so the area decreases, that means because stress is force or load upon area. So in this middle section, the area decreases because of this hole is cut out, so the area decreases. So if the area decreases, then the stress will increase. Okay, therefore it becomes sigma max. And when going from this center position to the corner, again the area keeps on increasing. As the area keeps on increasing, so the stress keeps on decreasing. So that is basically the stress concentration, that is the localization of high stresses due to the irregularities present, because this is the kind of an irregularity present, or also you can take it as the abrupt change in the cross section. Okay, so I hope you get the concept of stress concentration. As the area decreases or increases, the stress changes. But stress concentration is generally taken when the stress increases. That means the area decreases and the stress increases. Okay, so that is the concept of stress concentration. Let's move on forward. So in order to consider the effect of stress concentration and find out the localized stresses, because till now what we were doing in the subject of strength of material, we were just taking the load as static, so there was nothing like localization of high stresses. In all the cross section, throughout the cross section, we were taking the stress as same. and unless the force changes or the area changes, the stress was same. Okay, so to take this effect of stress concentration or the localization of high stress, what we do, we take a stress concentration factor. Okay, it is denoted by KT and is defined as follows. That is the highest value of actual stress near discontinuity. Discontinuity means the change in cross section, okay, or any abrupt changes, divided by the nominal stress obtained by elementary equations for minimum cross section. Okay, for minimum cross section, what we get for the nominal stress and the highest value, the ratio of these both these terms is given by KT, which is known as stress concentration factor. Okay, so this KT is sigma max upon sigma naught, or if it is a normal force, it will be normal stress, maximum normal stress upon nominal normal stress. Otherwise, it can be maximum shear stress upon nominal shear stress. Okay, these are the stresses determined by elementary equations, and these are the localized stress at the discontinuities. This is the term that is stress concentration factor. Okay, so now we have given that the stress changes or the stress increases, the localization of stress is there, due to which the stress concentration occurs. But what are the causes? We have to look into some of the causes, that what are the causes of stress concentration. They can be like this: variation in the properties of material. If there is some variation in the properties of material, like the internal cracks or flaws, like the blowholes are there, or cavities. In the case of weld, it is cavity. In the case of steel components, if there are air holes, or if there are some non-metallic or foreign inclusions, then the stress concentration occurs. Or basically you can say there is an abrupt change in the cross section, or the properties of the material changes in such a way that stress concentration occurs. Okay, then if in the case of load application, if there is a contact between the meshing teeth of the driving and driven gear, in that case also the stress concentration can take place. The other reasons are contact between the cam and the follower, okay, contact between the balls and the races of the ball bearings. These are the load conditions which can cause stress concentration. Next is the discontinuities in the component. What kind of discontinuities? See, certain features of the machine components such as oil holes or oil grooves, keyways and splines and screw threads result in discontinuities in the cross section of the components. Okay, so when there is discontinuities due to these many kinds of machine components like the oil holes, oil grooves, keyways, splines, screw threads, so in that case, when there is a discontinuity cross section, then stress concentration occurs in the vicinity or in the area which are close to these discontinuities. Okay, so these kind of discontinuities in the component also causes stress concentration. Then there are some machining scratches like the stamp marks, the inspection marks. Okay, these are the surface irregularities which also causes stress concentration. So these are some of the basic causes or basic reasons for the cause of stress concentration. Okay, then if there is a stress concentration, that means there is a localized high stress, that you have understood by now, but we have to minimize it. Okay, because if there is a high stress concentration, then there will be high stress, and high stress is not good for anyone. Okay, be it a machine component or be it human beings, high stress is not variable, because if you see yourself, when you are in a condition of high stress, when you are already tense due to 4 or 5 problems, then your mind, your efficiency decreases. That is same goes for the machine components also. When they are in a condition of high stress, they do not function properly and their chances of failure or fracture becomes more. Okay, so if there is a case of high stress concentration, because stress concentration will be there, because we have seen the causes. Okay, due to the changes, due to the properties of the material, the properties of the material will not be, any material will not be 100% means error free, or there will be not any material which will be 100% flawless. Okay, so there, because due to the limitations of the manufacturing and the raw materials that are used in the manufacturing of those components, the flaws and these kinds of discontinuities will occur. Okay, and also due to the designing part of some designing part or the design criteria, the design is such that the stress concentration will be there. So we cannot make it to zero, but we can minimize it. Okay, so there are some cases that I will tell you that how to reduce the stress concentration. Okay, so first is additional notches and holes in the tension member. Okay, if this is a tension member, if this is a member, but what is there? This notch is there. This kind of part is called as a notch. Okay, so notch is there. This is a member that is under tension. So due to this single notch, these are the lines, or we can say the stress lines, or the yes, these are the stress lines. Okay, so you see from here till here the stress lines are almost straight. Same goes for this side, but from here to here there is an abrupt change in the stress concentration lines. Okay, so due to this abrupt change in the stress lines, what will happen? There will be localization of high stresses, and the material is likely to fail at this region. Okay, so to reduce this, what we do, we make additional notches or holes. How? See this. This can be reduced in three ways. The first one is the use of multiple notches. So if we use multiple notches, then what will happen? The stress lines will not change abruptly. They will slightly keep on changing right down from here. Okay, from here, and they will keep on changing slowly and slowly. So the stress concentration will be minimized. Okay, I am saying minimized, but they won't be equal to 0. The second one is the same, that is the additional holes, the drilling of additional holes. If like this the holes are drilled in this, then also the stress lines will keep on deviating on a larger region. Okay, if they will keep on deviating on a larger region, then the stress concentration will be there, but it will again not be that much abrupt. Okay, so the chances of failure of the machine component is reduced. Okay, next is removal of the undesired material. If this much kind of material is removed, then also the stress lines do not change abruptly, and so the stress concentration decreases. Okay, next is, that was for the member in tension. But if you see now another kind of member, the member in bending. So for that kind of a member which is in bending, what we do? There are three methods. See, if this is a kind of a member, okay, so first of all, you see this is a member under bending, and this is a kind of a collar that is made on this member. Okay, why this collar is needed? This collar is needed for the sitting of the splines, okay, for the sitting of the gears, for the sitting of the pulleys, for the sitting of the screws. So for this kind of member which has got a shoulder, see at this region the stress lines are like this, and suddenly at this region, due to this change in the cross section, the stress lines suddenly changes, or there is an abrupt change in the stress lines, due to which the stress concentration occurs. So how to reduce that? There are three ways. First one is fillet radius, second is undercutting, and third one is notch. We will see them. See this. This is fillet radius. Earlier it was something like this. There was a straight line like this. But now what we have done, we have made this kind of a radius at this. This is known as a fillet radius. Okay, due to this, the stress concentration lines do not changes their direction abruptly, and due to which the stress concentration effects are minimized. Second one is undercutting. Undercutting means we have removed this much material. This much material has been removed. So again, the stress concentration lines, which was earlier somewhat like this. Okay, earlier the lines were like this, as I have shown in red. Now they have become like this. Okay, this shown in black. So the stress concentration line does not changes abruptly, and again the stress concentration is reduced. Third one is additional of notches. Here we have added a notch. Okay, here we have added a notch, and also we have given the fillet radius here. As you can see, this is the fillet radius. Okay, this is the fillet radius, and also we have given the additional notch here. So due to this also, the abrupt change does not occur, and hence the stress concentration reduces. Okay. See, if this is a shaft, this is another case. If this is a shaft, this is a keyway that has been made on the shaft. This is a keyway. Keyway means, if you do not know what is a keyway or what is a key, basically key is an element that is used to connect two elements. If this is a shaft over which a pulley is to be seated, so this key will hold the shaft and the pulley together. Okay, this much is enough for you right now for keys. We will take a separate lecture, complete separate lecture on keys also. Okay, so for sitting of the key, there has to be a keyway. both on the shaft also and on the pulley also. So we are showing this for the shaft. So for the shaft, this keyway causes the change in the cross section. Okay, so change in the cross section means the stress concentration lines or the stress lines decreases or changes its direction right down like this. From here till it was like this, and then it suddenly changes its direction due to this keyways. Okay, so what is to be done? We can drill these kind of holes from here so that the stress concentration lines which were earlier going somewhat like this, okay, which were earlier going somewhat like this, now they become somewhat like this. Okay, they are shown in black. So the stress concentration line do not changes abruptly, and hence the stress concentration effects are reduced or minimized. Okay, then another case of threaded members. What about the threaded members? We have seen for the members under axial load or tension, the members under bending, the shaft in which the keyway is present. Now comes for the threaded member. If this is a kind of a threaded member, we see this is the shank. This portion is known as, this whole portion is known as the shank. Okay, and then this is the threaded portion, okay, at which the threads are present. So in this case also you can see the stress lines abruptly changes as the threaded region begins. Okay, so to how to minimize the effects of stress concentration, the first one is the undercutting. Undercutting means at this region we have undercut, at this is like this, we have done it like this, so the stress concentration lines would go somewhat like this as shown here. Okay, so if they go like this, then the abrupt change is not there, and also the stress concentration will be reduced, and also we can provide a kind of this thing, that is the fillet radius. So this will also give you the same effect of reducing the stress concentration. The next one is the reduction in shank diameter. Earlier the shank diameter, if you see in the previous slide, it is somewhat like this. Okay, the shank diameter is somewhat like this, means this is also the shank diameter. But now what we did, we reduced the shank diameter to this much, okay, so that the stress lines goes straight. Okay, that is also the way to reduce the stress concentration or to reduce the abrupt changes in the direction of the stress flow lines. Okay, so this was all about the stress concentration and how to reduce the effects of stress concentration. Now we come to the main topic with which we started the chapter, or what is basically the whole core area of this chapter, that is the fluctuating stress or the fluctuating loads. So let us see that. Fluctuating stresses. Stresses induced due to the forces which vary in magnitude or direction or both. So the fluctuation in the stresses can be due to the variation in the forces either in magnitude or in direction or both. Okay, and that is too with respect to time, and they are called fluctuating stresses. Okay, so if it is a fluctuating stress and the forces or the stresses are varying with respect to time, so there has to be some model for stress time relationship, and the most popular model that we use is the sine curve. These kind of questions can also come in the theory part, that for the case of a fluctuating stress, the most popular model or the most commonly used model for stress time relationship is sine curve. Okay, so these are three kinds of fluctuating stresses. The first one is fluctuating or alternating stresses, second is repeated stresses, and third one is reverse stresses. What are those? Let us see one by one. First one is fluctuating stresses. This is the stress time relation. This is the sinusoidal curve, okay, that shows the stress time relation. This stress has a maximum value at some point of time, this, and a minimum value at another point of time, this. Okay, so that is the stress, the fluctuating stress, that is fluctuating between some maximum and a minimum value. Okay, so in this we define two terms. One is mean stress, that is given by half of sigma maximum plus sigma minimum, and another one is stress amplitude, that is half of sigma maximum minus sigma minimum. So these two terms you must know, what is mean stress and another one is stress amplitude. Okay. Next is the case of repeated stress. In the case of repeated stress, the minimum stress is 0. Please remember these conditions also. They are also very important. Okay. So if mean stress is 0, means minimum stress, not mean. Minimum stress is 0 because we know mean stress is equal to 1 by 2 maximum plus minimum. Okay. And stress amplitude is equal to 1 by 2 maximum minus minimum. Okay, in the case of repeated stress, the minimum part is 0, so the mean stress and the stress amplitudes are both equal to sigma max by 2. Okay, the third case is the reversed stress. In the case of reversed stress, the mean stress is 0. Okay, the mean stress is 0. This is the case for mean stress. So if mean stress is 0, then sigma minimum is negative of sigma maximum. Negative means the magnitude is same, but it is in the opposite direction. That means if the maximum stress is in tensile, having some suppose the maximum stress sigma maximum is equal to 50, suppose 50 megapascal, then sigma minimum will also be 50. Okay, but if this is tensile, then this one will be compressive. This is the only point. Okay, that means they are same in magnitude but just opposite in direction. Okay, so the stress amplitude will be equal to half of maximum minus minimum. Okay, since these two are same, so the value you can take it as maximum by 2 or minimum by 2. Both will give you the same numerical value. Next is the case of fatigue failure. Okay, so what is fatigue failure? The materials fail under fluctuating stresses at a stress magnitude which is lower than the ultimate tensile strength of the material, and sometimes it is even lower than the ultimate yield strength, because we know in the case of static loading, the materials either fail at the value which is near to the ultimate tensile strength or the yield strength. But in the case of a fluctuating stress, due to the fluctuation of stress that the material or the component is bearing, these materials or these components fail under the stresses which are very less than these yield or ultimate value. Okay, and also it has been found that the magnitude of stress causing failure decreases. Okay, the magnitude of stress causing failure decreases as the number of stress cycles increase, because one maximum, one minimum, that together causes, if you see like this is time and this is a stress, and if the stress is varying somewhat like this, okay, because maximum minimum it will vary, so this one maximum and one minimum will cause one cycle. Okay, from here till here it will be one cycle, then again from one maximum to another maximum it will be another cycle. So as the number of stress cycles increases, then the stress at which that failure occurs further reduces down. Okay, so this phenomena of decreased resistance of the materials to the fluctuating stresses is the main characteristic. This is the main characteristic of fatigue failure. Okay, and fatigue failure is defined as the time delayed fracture under cyclic loading, because this is a cyclic loading, and the time delayed fracture means as the time progresses the number of cycles will increase, and if the number of cycles will increase then the failure stress will further reduce, and so that kind of failure is known as fatigue failure. Okay, and the fatigue failure depends upon the number of factors such as the number of cycles, the mean stress, the stress amplitude, stress concentration, residual stresses, corrosion and creep. So these are some of the factors upon which the fatigue failure depends. You have to remember these terms also, because these kind of questions can even appear in the theoretical part of the examination, that which of the following is or are the factors or not the factors responsible or on which the fatigue failure depends. So you have to remember these types of theory parts also. Okay. Then is, for this case, there comes a term that is known as endurance limit. Okay. The fatigue or endurance limit of a material is defined as the maximum amplitude of completely reversed stress that the standard specimen can sustain for an unlimited number of cycles without fatigue failure. Okay. So it is the maximum value of the maximum amplitude of the completely reversed stress. Okay. Because when the material or a component is under cyclic loading, there will be some stress amplitude, and the maximum value of that stress amplitude that a material can withstand while undergoing the cyclic loading for unlimited number of cycles without any fatigue failure is that is known as endurance limit. But the unlimited number of cycles does not have any sense, because any material will at some point of the time or other will cause, there will be failure in it. Okay, there will be failure, there will be fracture, because no material or no component can withstand the unlimited number of cycle or cannot have a life cycle of infinity. Okay, so that unlimited number of cycles has been taken as 10 to the power 6 cycles. Okay, 10 to the power 6 cycles. So that is the endurance limit. Now what is fatigue life? A fatigue life is defined as the number of stress cycles that the standard specimen can complete during the test before the appearance of the first fatigue crack. So before the appearance of the first fatigue crack, what are the number of stress cycles that a standard specimen or a standard component can withstand? That is known as fatigue life. Okay. So in the laboratory, the endurance limit is determined by the means of a rotating beam machine. This is the name of the machine which was used for determination of endurance limit, and this machine was developed by a scientist named as R.R. Murray. Okay, and the result of this test are plotted by the means of an SN diagram. Okay, SN diagram, S means stress, N means the number of cycles. So the results have been plotted by the means of an SN diagram. Okay, so what is that SN diagram? The SN curve is the graphical representation of stress amplitude. This is stress amplitude versus the number of stress cycles. These are the number of stress cycles before the fatigue failure on a log graph paper. This graph paper is not a simple graph paper. This is a log graph paper. Being an engineer, you might be aware of what is a log graph paper. Okay, if you are not aware, just go to the Google and search it out. What is a log graph paper and how is it different from a normal graph paper? Okay, you will see this. Okay, so this is the kind of a figure or the SN curve that we get. But this kind of SN curve is valid only for ferrous material. This is not valid for non-ferrous material. If you can pause a video for a minute or two and just draw this diagram, and what all is written, you just draw this. I will explain it further. What are all these things? Okay, so you just pause the video for a minute or two and just draw this diagram. So for ferrous materials, I have told you this, for ferrous materials like steels, the SN curve becomes asymptotic at 10 raised to the power 6 cycles. Asymptotic means the SN curve, the curve becomes parallel to the normal axis, means the x-axis or the number of stress cycles axis, which indicates the stress amplitude corresponding to infinite number of stress cycles. That's why the infinite number of cycles has been taken as 10 to the power 6 cycles. Okay, and the magnitude of this stress amplitude as 10 raised to the power 6 cycle represents the endurance limit of the material. So now you come to know that how that value or why that value of 10 raised to the power 6 cycles has been taken for the determination of endurance limit. Okay, for this, but this was only the case for the ferrous materials. Okay, so for non-ferrous materials like aluminium alloys, the SN curve slopes gradually even after 10 raised to the power 6 cycles. So these materials do not exhibit a distinctive value of the endurance limit in a true sense. So for these materials, endurance limit stress is sometimes expressed as a function of the number of stress cycles, because for these, see, if this is a kind of diagram, or let me explain it in the earlier one only. This is the curve for ferrous. This becomes asymptotic or the parallel to this x-axis at 10 raised to the power 6. But for the non-ferrous materials, what happens? The curve is gradually comes down like this. Okay, so there is no definite value of the endurance limit for the case of non-ferrous. This one is for the ferrous. Okay, this whole is for the ferrous and this bottom one is for the non-ferrous. Okay, but in the examination, if the question comes, that will be from the ferrous only. Okay. Next is, there are two kinds of loading on this also. One is high cycle and one is low cycle fatigue. What are those? See, this is again the diagram. Earlier one we haven't drawn it from, we have drawn it from 10 raised to the power 3 only till 10 raised to the power 8. But now we are drawing it right down from here. Okay, from 0 to 8, that means 10 raised to the power 0 to 10 raised to the power 8. So from 0 till 3, that means from 1 to 10 to the power 3, that means 1000 number of cycles, the stresses that are induced are known as low cycle fatigue, and above that they are known as high cycle fatigue. Okay, and the slope, you can also have to note down the slope, that this slope is less and this slope is more steeper, because this value, there is also a difference of 3 here and there is also a difference of 3 here. Okay, so the slope is more for the case of high cycle fatigue. These kind of questions may also come in any examination. Okay, the slope of which curve is higher, whether it is a high cycle fatigue or a low cycle fatigue. Okay, so you have to see these diagrams also very carefully. Okay, this I have written also. There are two regions in this curve, namely the low cycle fatigue and the high cycle fatigue. Any fatigue failure when the number of stress cycles are less than 1000 is called low cycle. Okay, and these components which are subjected to the low cycle fatigue are designed on the basis of ultimate tensile strength or yield strength with a suitable factor of safety. Means they are simply designed as the case of a static loading. And any fatigue failure when the number of stress cycles are more than 1000 is called high cycle fatigue, and the components which are subjected to high cycle fatigue are designed on the basis of endurance limit stress. Now comes the role of endurance limit stress in the case of high cycle fatigue. Okay, so the SN curves, the Soderberg lines, the Gerber lines or the Goodman diagrams are used in the design of such components. You might have listened to these names before, the Soderberg, Gerber, Goodman lines and all. Okay, so they are used for the case of high cycle fatigue when the number of stress cycles are more than 1000. Okay, now we will see what are those lines. Okay, just in a while, but first of all, let us touch one more important concept, that is known as notch sensitivity. We will see up that one also. Okay, so first of all, let us just see this one, that is what is notch sensitivity. Notch sensitivity is defined as the susceptibility of a material to succumb to the damaging effect of the stress raising notches in the fatigue loading. That is, this is just a bit of a technical language. Just understand it this way, that if there will be a notch, okay, if there will be a notch, then what will happen? Then there will be localization of high stresses due to stress concentration. Okay, so this notch sensitivity somewhat defines that thing only. Okay, how? That is, increase of actual stress, this Q is the notch sensitivity. Okay, you can write it down here also that it is defined by Q. So this Q is increase of actual stress over nominal stress divided by increase of theoretical stress over nominal stress. Okay, so if this sigma naught defines the normal stress or the nominal stress, so the actual stress will be this and theoretical stress will be this. Okay, this we have already seen, KT. So this is the theoretical stress and this is for finding out the actual stress. Okay, so therefore Q is equal to this way, this sigma naught goes cancel from everywhere, so that becomes Kf minus 1 upon Kt minus 1, and if we simplify this equation we get Kf is equal to 1 plus Q times KT minus 1. Okay. And when the material has, now arrives the two conditions, we have written that Kf is equal to 1 plus Q times KT plus 1. Okay. Sorry, KT minus 1. Like this it is here, KT minus 1. Okay. So when the material has no sensitivity to notches, that means the Q is equal to 0. In that case, the Kf will be 1. And when the material is fully sensitive to notches, then Q will be equal to 1. So this Kf will be equal to KT. Okay. The magnitude of notch sensitivity factor, yes, you can see it from 0 to 1. This varies from 0 to 1. And the notch sensitivity is varies. It varies for various materials and also varies for various kinds of loading conditions. Okay, for various materials, for reverse bending or axial stress and reverse torsional shear stresses varies. It means that the notch sensitivity is not same if you are taking same material, but that same material is undergoing different kinds of stresses conditions or different kinds of loading conditions, then also the notch sensitivity factor will change or will vary. Okay. But if in case of a doubt, means the designer does not know whether this material has sensitivity to notches or not, then he should use Q is equal to 1, in which case this KT will be equal to KF and the design will be on the safe side. Whether in case of a doubt, you can use the value of notch sensitivity factor equal to 1. Okay. Now the endurance limit approximate estimation. Okay, see, there are two types of endurance limit stresses that we have defined. One is SE dash, that is the endurance limit stress of a rotating beam specimen subjected to reversed bending stress. Okay, and this is the endurance limit stress of a particular mechanical component. This is for the rotating beam specimen that we were that has been used in the laboratory for finding out the endurance limit, that is designed by R.R. Murray. So that is basically, that is the SE dash, that is the endurance limit stress of that component, that is the rotating beam specimen, and this SE for the particular mechanical component. That means this is basically a standard specimen. Okay, this is a standard specimen and this is for any component or any specimen for which we need to find out the endurance limit. Okay, so this SE is equal to Ka, Kb, Kc, Kd into SE dash. What are these terms? Ka is surface finish factor, Kb is size factor, Kc is reliability factor, and Kd is the modifying factor to account for stress concentration. Okay, so we will not go into means greater detail of on all which of these factors, that these terms, that the surface finish factor, size factor, reliability factor and all these, on which other things or on which other dimensions or on which other properties these factors depend. We will not go into that much detail because that has not been asked in any examination till now, and there are the chances of being that asked is also very less. So but still, if you want to have an idea or if you just want to clarify your doubts, if any, so you can just go to that. You can either find these terms or more detail about these terms in any standard books, okay, or also you can go to the internet and just find it out. But it is not advisable to waste your time on that things because that is not going to be asked in any examination, okay, and the time is also very less, so you have to be focused on these things. Okay, so just try to do this much only. Next is, now comes the reversed stresses, the design for finite and infinite life. Okay, two types of designs are there. One is finite life and another one is infinite life. First one, when the component is to be designed for infinite life, the endurance limit becomes the criterion of failure. So you have to remember that when any component is to be designed for infinite life, the endurance limit becomes the criterion of failure. Okay, so such components are designed with the help of the following equations: sigma A equal to SE by Fs and tau A equal to SSE by Fs, where this sigma A and tau A are stress amplitude in the component and SE and SSE are the corrected endurance limits in reversed bending and torsion respectively. Okay, these are the terms that are given. these are the stress amplitude and these are the corrected endurance limits. Okay, in reverse bending, this is for bending and this is for torsion. Next comes the second case, when the component is to be designed for finite life. Then the SN curves are used. Okay, this curve is valid only for steels, as I have told you. It consists of a straight line AB. This is a straight line AB drawn from 0.9 SUT at 10 to the power 3 cycles to SE, point this to this. That is to SE at 10 to the power 6 cycles on a log paper. Okay, this. Next, what is the procedure? The procedure has been written here. So first of all, you have to locate a point with this coordinate. Okay, then you have to locate a point B with this coordinate. This is the simple standard procedure for solving these kind of problems. Okay, so you have to first determine A point, then B point, then just join these 2 points. Okay, and this line is used for the criterion of failure for finite life, not for infinite life, for finite life. Then depending upon the life n of the component, we have to draw a vertical line like this. See this. If this is n, so we have to draw a vertical line like this of the component through this on the abscissa. This line intersects AB at F. As you can see here, this is intersecting AB at F. Then draw a line FE parallel to the abscissa, that is the x-axis. See this, like this, this is parallel FE. Okay, the ordinate of the point E, that is log 10 SF, gives the fatigue strength corresponding to n cycles, and then this value of fatigue strength F is obtained by the above procedure. This is used for the design calculations. Okay, so this is a standard procedure for solving this part of a problem. We will try to solve the problem when we will see the section on the previous year solved problems. Okay, if there has been any question asked, that will be solved. If it is not asked, then because in this subject, what is there, not many questions have been asked in the gate examinations. Okay, so the topics which will be really important and for which the chances of questions appearing in the examinations will be high, for them I will try to take some examples for you, the numerical examples, and there I will be trying to solve them for you. Okay. Next comes the cumulative damage in fatigue. When the mechanical components are subjected to different stress levels for different parts of the work cycles, that means the stress levels are not same. Okay, the life of such components is determined by one equation that is known as Miner's equation. Okay, suppose a component is subjected to completely reversed stresses, sigma 1 for n1 cycle, sigma 2 for n2 cycles, and so on. That means the stress levels are different. Then let capital N1 be the number of stress cycles before fatigue failure, if only the alternating stress sigma 1 is acting. That means this is the number of stress cycles before fatigue failure if only sigma 1 is acting. Okay, then one stress cycle will consume 1 by n1 of the fatigue life. Okay, because this is the total life, so one cycle will consume 1 by n1 of the fatigue life, and there are n1 such cycles, because if sigma 1 is acting, the number of cycles are n1. So if one cycle will consume this much life, then n1 cycle will consume how much life? This cycle will consume n1 by n1 life, and similarly for sigma 2 it will be n2 by n2. So that just adding these, we get the total life as equal to 1, and this is the basic Miner's equation. Okay, and sometimes the number of cycles n1, n2 at stress levels are unknown, but what we are given that alpha 1 and alpha 2 and so on are the proportions of the total life that will be consumed by the stress level sigma 1, sigma 2. There, suppose there is the total life is n, and the total life is n, and the n1 means the sigma 1 stress will be there for n1 cycle, and n1 will consume alpha 1 of the total, means alpha 1 proportion of the total life. So this will become like this, and for n2 this will be like this, and similarly for others also. So substituting these values in the Miner's equation, just n1 and n2, if we substitute it here, what we get? We get this way. Okay, and also this alpha 1 plus alpha 2 plus alpha 3, because if n1 cycle is there for 0.2 of n, okay, n2 is equal to, means this is 0.2 times, 0.2 is the proportion or the percentage, 20%. Suppose this is for 30%, n3 is equal to 0.4 and so on. So this alpha 1 plus alpha means these are the alpha values, okay. So alpha 1 plus alpha 2 plus alpha 3 will also become equal to 1, like this, okay. So by these equations, the life of the component subjected to different stress levels can be determined, okay. This was all about the cumulative damage in fatigue. Now comes the three lines that I was talking about. The first one is the Soderberg, second is Goodman, and third one is the Gerber lines, okay. Now you pause this video for a minute or two and just carefully draw all these lines, okay. This is the mean stress on the x-axis, this is the stress amplitude on the y-axis. Just draw these diagram very carefully, all the lines, the Goodman line, the Soderberg, the Gerber line, the yield line, the failure points, all have been shown here. Just pause a video for a minute or two, take your time and carefully draw this diagram. Then we will proceed further. See this, the Soderberg line. The Soderberg line, it is a straight line joining SE on the ordinate, that means y-axis, and SYT on the abscissa. So this equation becomes like this, okay. This is a similar simple geometrical equation for this, and if Fs is the factor of safety, then Soderberg equation will become like this, okay. There is nothing much to be explained on this. This is sigma mean stress, and this is stress amplitude. For the Goodman line, the straight line joining SE on the ordinate and SUT on the abscissa. Here it was SYT, here it is SUT on the abscissa. Other points are same for the Goodman and the Soderberg line, okay. So in case the equation is like this, in case of factor of safety, the equation changes this way. Then comes the Gerber line or the Gerber curve. It's a parabolic curve. You have to remember that Soderberg and Goodman are the straight lines, whereas the Gerber line is a parabolic curve. So the Gerber line, it's a parabolic curve joining SE on the ordinate and SUT on the abscissa. So the equation becomes like this, okay. And if Fs is the factor of safety, then the equation changes to this form, okay. You have to remember these standard equations because the questions based on these equations are very frequently asked in the examination. Not if in the gate examination, the chances of them being asked is really high. So you have to remember these equations. Next comes the modified Goodman diagrams. There are one more concept of, these were the three standard diagrams or the standard lines, the Soderberg, Goodman and the Gerber were what, but there comes one more type of diagram, that is the modified Goodman diagrams. And one question has even been asked in 2018 based on this modified Goodman diagram. So that has to be covered. We cannot leave this topic, okay. So for the purpose of design, the problems are classified into two groups. First one is components subjected to fluctuating axial or bending stresses. First. Second is subjected to fluctuating torsional stresses. For both these cases, the two kinds of diagrams are used. One diagram cannot be used, two diagrams have to be used. We will take them one by one. This is the first one, the component subjected to fluctuating axial or bending stress, okay. This dotted line till here, from till here, this means this DC line is the yield line, and this SE and joining SUT, this one is the Goodman line, okay. And this line, this A, B, C region, this is the modified Goodman region or the region of safety, okay. How this diagram is drawn, you just draw this and let us see what are the important points related to it. The Goodman line is modified by combining fatigue failure with failure by yielding, okay. The yield line DC is constructed by joining SYT on both the axis, abscissa and ordinate, means SYT on the x-axis, SYT on the y-axis, that is the yield line. Then the Goodman line is constructed as usual, joining SE on the ordinate and SUT on the abscissa, and the B is the point of intersection of these two lines. So this OABC represents the region of safety, and this region is called the modified Goodman region. This is just the basic about this about this diagram, okay, the modified Goodman diagram for the case of component subjected to bending, okay, not for torsion, just for bending. So the question on this will be taken up for you okay, as an example, or if there is one question that has been asked in the GATE 2018, that will be taken up for you. Then this concept will become really clear, because solving a question in the middle of a lecture class, that will already this lecture has gone too long, okay. So if we will solve the problem, then again it will take 5 to 10 minutes. So that is not good. Here we will take it in a separate lecture on the previous year solved problems section. Okay, the next one. Okay, on in this also there are some important other points also. Tan theta is given as sigma A by sigma m, that is amplitude, stress amplitude by mean stress. Okay, and the point of intersection of line AB and OE is the straight line that have the slope of tan theta is x. Okay, and this point x indicates the dividing line between the safe region and the region of failure. Okay, and the coordinates of the point x, that is SM and SA, this is x, this is y, represent the limiting value of stresses which are used for calculate the dimensions of the component. And the permissible stresses are as follows, like sigma A equal to stress amplitude equal to SA by Fs, and sigma mean equal to SM by Fs. So this is how the design is done using the modified Goodman diagram. Next one is the component subjected to fluctuating torsional stresses. In that case, the diagram becomes somewhat like this. The torsional mean stress is plotted on the abscissa. This is the torsional mean stress, and the torsional stress amplitude is plotted on the ordinate. The torsional yield strength, that is SSY, is plotted on the abscissa, this point, and the yield line is constructed which is inclined at 45 degree to the abscissa. So this line will again go here, okay, and this will join here. This point will again be SSY. So this will be a yield line at an angle of 45 degree. Okay, the torsional mean stress has no effect on the torsional endurance limit. Okay, the torsional mean stress does not have the effect on the torsional endurance limit. Therefore, a line is drawn through SSE on the ordinate and parallel to the abscissa, like this. This is a line that is drawn from the point SSE, and that is parallel to the abscissa or this x-axis. Okay, the point of intersection of this line and the yield line is B. You can see here this line and the yield line, the point of intersection is B. Then the area OABC represents the region of safety. The fatigue failure is indicated if this tau A, that is the torsional stress amplitude, is equal to SSE, and the static failure is indicated if tau max is equal to stress amplitude plus mean stress. Means stress, torsional stress amplitude, and torsional mean stress is equal to SSY. And the permissible stresses are as follows, that is tau A equal to SSE by Fs and tau max equal to SSY by Fs. Okay, that is the endurance value and this is the yield value. Okay, so this is all that is for this lecture on the design of fluctuating loads. Each and every question that will be asked in the examination, that will be solved by this much theory only, because this is all that is covered, or this is to be covered for this examination. Just you need to do is you need to solve problems based on these topics. Okay, the lines topic, the Soderberg, Goodman, Gerber, these are very important concepts, and also based on the SN curves. The questions have been asked in the past and you are requested to please solve the questions based on this topic. Okay, so attempt the quizzes, the mocks, the test series that we are providing you on the Gradeup app. And if you have any problems, any queries, you can write to us. Your feedbacks are always welcome. So see you in the next class with another topic. Till then, thank you, take care, bye.